Good morning. The aim of this talk is to show you the scientific value of crowdsourced data in seismology. I want to show you they are not anecdotal data, but they can really make a big difference in operational seismology. Seismology has always been interested in eyewitnesses observation. This is typically the case for historical seismology. There was a revolution with the internet when the USGS opened the Did You Feel It system and suddenly put the traditional questionnaire online. It allows massive collection of information and automatic processing. There was a second revolution, which is with the smartphones, mobile devices. This is here illustrated by the Lastquake app, and suddenly we can collect comments, we can collect geolocated pics and videos, we can link to the social networks, and rather than a questionnaire, we replaced it with a set of cartoons depicting different shaking and damaging level, and then erasing all language barriers. Smartphones are a revolution because they are available anytime, anywhere, and of a very precise location. And in seismology in practice, it means they turn eyewitnesses in real-time shaking sensor. This is here on the left the Samo earthquake, and the orange dots represent when Lastquake app users open it to find out information. You have the time on the top at the bottom, and you have the PNS propagating waves. And as you can see, basically the openings mimics the propagation of the waves. So basically people are real-time sensor, and if you are not convinced, you can see exactly the same data in a time distance plot, and you see that compared to the P wave, the fastest reacting users open the app within typically 20 seconds. So one can say, yes, but it is purely anecdotal. Not exactly. First, if you monitor the number of people opening the app, this is the bottom left, you can have what we called crowdsourced detection. So the red curve is the curve of people opening our app, and you see that's within here, that's 15 seconds, we have a large surge, and you can locate where it's felt, so you know before you get any seismic location where the earthquake is felt and when it was felt. We have two other crowdsourced detection methods, which is the one developed by USGS, monitoring the number of tweets on Twitter. So when people, like example in California, say, "Oh my God, earthquake," so you have the curve here. And on the top, this is the monitoring of the traffic on our website. But basically, you can detect earthquake with no seismic data and faster than the vast majority of seismic network. But it is not the only benefit. We have developed the methods called CSLock for crowd-seeded seismic location, which is the combined analysis of crowdsourced and seismic data for very fast and accurate seismic location at global scale within typically 1 minute. So when you have a crowdsourced detection, you have a location. Here it is represented on the left by the blue star. You use this location to select the stations in triangles which may have recorded the earthquake. You use the time of this crowdsourced detection to extract the proper time window. You look at the pics, and you launch, once you have get rid of the outliers, you launch a seismic location, and the location in this case was in central Italy, like the red star. The advantage of this is that you have nothing to change in your network, but at the moment, if you compare, we have typically 5 minutes to produce our first preliminary location at EMSC. For the same earthquake using CSLock, we are at 1 minute, and we are currently working by integrating on the integration of the data from the Raspberry Shakes. But of course, CSLock may not provide you a magnitude estimate systematically. So what can we say about the size of the earthquake? Then we turn to the surface of the felt area as measured by the people launching the app. So what I showed you for the Samo earthquake. So on the left, there are the surface area, square kilometer, in logarithm scale for 3 magnitude earthquakes. So in green, magnitude is missing, but it's 2 point something in Croatia. So you see So basically there is no increase, rapidly no increase of the size, simply because all the eyewitnesses have felt the quake at the same time. And of course, if you take a magnitude 7, the surface of the felt area is much bigger. So we are training an artificial intelligence tool to see whether it can make a difference. And basically, currently, it's still in progress, but currently it works in 60% of the case. So we put the threshold at magnitude 4, and typically within 2 minutes of the quake, it is able to tell us whether it's a small, so well below 4, or larger earthquake. Of course, we also collect felt reports, so which report the felt experience of eyewitnesses. Here it is for the Petrinja earthquake, 16,000 felt reports collected. So individual felt reports represented on the left are in blue on the right. So you see they are at the same distance, huge variability, which is illustrated by the standard deviation, also represented. But basically, if you look at the average, you see that it does depict the seismic attenuation, the intensity attenuation with distance very nicely. Then these felt reports do have information about the shaking level, and the USGS, Vince Quitoriano and Dave Wald, have been working now to ingest automatically our felt reports. So this is for the Petrinja earthquake. This is with Did You Feel It only, the EMSC only, and the one for field survey. So basically, it is in progress and it will be available to all. We are also developing a real-time exchange tool, so any institutes will be able to receive our felt reports in real time if they want to ingest them in their own shake map. Another way to use these felt reports is to extract source parameters. This is developed by Paolo Gasparini and Gianfranco Vannucci. It is called Boxer. So basically they take the individual data points, so the felt reports, they create macro seismic data points. And for example, for this earthquake in Kashmir, we had no seismic location for more than 40 minutes, but using this approach, we could have the location 6 kilometers after the earthquake, and within 12 kilometers the final location. Another development has been made with Maren Bose at ETH in Zurich. She has developed Finder. Finder is a software which uses axiometric data to rapidly determine the rupture geometry of large earthquakes for early warning systems. So axiometric data were replaced by felt reports to see whether these felt reports could help us defining the strike, length and position of the rupture, which is absolutely key for rapid impact assessment. And it works, especially for strike slip events. We are currently ongoing tests in operational conditions. There are more results presented here in a poster for the Haiti earthquake. Concerning the damage, we have put in evidence what we call the donut effects. It means that initially the crowdsourcing rate from damaged area is much lower than the crowdsourcing rate observed for this specific earthquake. What are the implications? If you do not collect data from damaged area, it means that your epicentral intensity is likely to be initially underestimated. It is illustrated here on the right. You have the dashed line representing the number of felt reports collected in the epicentral area of the Petrinja earthquake, and you see that initially, so the red curve, initially it was an intensity 8, and gradually after an hour it increased to intensity 9, simply because we collect more data from the damaged area. It can also be seen, you have exactly the same curve here on the left for the Albania earthquake, and what it means in practice, when we detect these donuts, or this lack of data, we know that we have to be very careful about the initial value of the epicentral intensity, and we probably have to wait nearly an hour to get it. So basically, this donut effect is a heads up. We monitor the intensity, and you see even for earthquakes in the middle of the night, you can see on the right that we start collecting picture. It is also for the Albanian earthquake within basically an hour, and sometimes even much faster. So again, these data allow us to build our knowledge about the actual impact of the earthquake. These pictures can also be used to make a remote survey. This was performed for the Zagreb earthquake by Diana Contreras from the University of Newcastle. So she took all our geolocated pics and see what can be observed from distance about the actual impact of the earthquake, as the field survey which was planned was not possible due to the COVID. Following this study, we have modified and we have improved our collection tool, and we believe that it can in the future help to make this type of studies more systematic. I cannot have a talk about crowdsourced data without mentioning EQN, which is a smartphone app developed by Francesco Finazzi at the University of Bergamo, and it is the first app which has delivered public earthquake early warning. The principle is pretty simple. When your phone is charging, it turns your smartphone in a seismic detector. When you have concomitant detection, so basically smartphones which are close vibrating at the same time, you send a warning. There is a presentation about the results, and you will see the results are impressive. I hope I have convinced you about the value of this crowdsourced data, from earthquake early warning to damage assessment. This field is also moving extremely fast and changing extremely fast, simply because the volume of data we collect is increasing very rapidly, and it will increase even faster with the development of the Internet of Things. And it also opens new fields, and I will just take this example that I didn't illustrate so far. It offers a link between seismology and humanities. We have a linguist who works on the comments we have collected during an aftershock sequence, and to see how the narrative about earthquakes changes among the public during this time period. We have also tested the possibility to make sentiment analysis from these same comments to see whether we can have a proxy for measuring the time variation of anxiety level. So it is a new field, it is developing very fast, and you are very welcome to join us. Thank you for your attention.